We're going to wrap up Chapter 8 by looking at improper integrals. And improper integrals can be of type 1 or type 2. Type 1 would be like picture A here, where either the upper or lower bound is going to go to infinity or negative infinity, or sometimes even both of them. Type 2 is the case of that picture B there, where the graph itself, the curve itself, is going to go off to infinity. And we're going to learn some techniques to be able to integrate in either of these cases. But we're going to start with the first case, those improper integrals of type 1, and we're going to use limits to help us. Now, depending on whether the upper or lower bound goes to infinity or negative infinity, we will substitute with either an A or a B and then take the limit of that integral as either A goes to negative infinity or B goes to infinity. If both the upper and lower bound go to infinity, so the one goes to negative infinity, the other goes to positive, then you can split it up. Just find some point C in the middle, a point C that's convenient, and we'll do an example of this later. And then you just basically combine the first two parts there. If the limit exists and it's a finite number, we say that the integral converges. And then that limit is going to be the value of the integral. But if the limit fails to exist, we say that the integral diverges. And so we're going to do several examples of this just to show you how it works. The first one, we're going to look at a very commonly used family. We've got basically 1 over x to the p power. It says, for what values of p does the integral from 1 to infinity of dx over x to the p converge? When the integral does converge, what is its value? So this is going to take just a few minutes to go through. And what I'm going to do is I'm going to start out by assuming that p is not equal to 1. We're going to look at that very special case by itself later. So I'm going to start by assuming that p is not 1. It's either something larger than 1 or something smaller than 1. So what I'm going to do now is I'm going to set up this integral as a limit. So instead of having it go from 1 to infinity, I'm going to have it go from 1 to b, and then we're going to look at the limit of that integral as b approaches infinity. So let me go ahead and write this out. So again, we're going to take it from 1 to b and look at that as b, look at the limit as b approaches infinity. Now, we can integrate this. 1 over x to the p is the same thing as x to the negative p power. So we can integrate, and I'm going to do that real quick. Let me keep my limit out here. When we integrate, we get x to the negative p plus 1. So remember, this is x to the negative p power. So when we integrate, it's x to the negative p plus 1 over negative p plus 1. And we will evaluate that from 1 to b. Now, the negative p plus 1 in the denominator, that's going to be a constant. So I'm going to go ahead and pull that out. When I pull that out, I'm going to rewrite it. Negative p plus 1 is the same thing as 1 minus p. So I'm going to look at it as the limit as b goes to infinity of 1 over 1 minus p. Now, if I plug in a b for x, I get b to the negative p plus 1 minus 1 to the negative p plus 1, but 1 to anything is still going to just be 1. So we're looking at the limit of this whole big thing here, and we just really need to focus on the b, because it's b that's going to infinity. Well, what this ultimately is going to come down to is looking at the exponent here and whether it's a positive or negative value, okay? All I assumed at the beginning is that p is not equal to 1. So p could be something like 4, in which case this would be negative 4 plus 1, or b to the negative third power. And if you had something like that, b to the negative third, it'd be 1 over b to the third. Well, as b goes to infinity, that would go to 0. And that would be all well and good. We could easily take the limit. But what if p is something smaller than 1? What if p is negative 2? Then we'd have negative 2 or positive 2 plus 1. That'd be b to the third power. Well, as b goes to infinity, so would that. So we need to further break this down. So I'm going to start by saying if p is greater than 1, then negative p plus 1 is going to be less than 0. So again, if p is larger than 1, so p could be even 1.5, anything, as long as p is larger than 1, then this exponent is going to be less than 0, in which case we've got 1 over b to some power, and that limit as b approaches infinity will go to 0. So if p is greater than 1, negative p plus 1 is less than 0, and then the limit as b approaches infinity of b to this power, so again, it's b to a negative power, equals 0. I apologize that I'm going slightly downhill as I write this. So if p is greater than 1, then this goes to 0, and our entire limit becomes negative 1 over 1 minus p, or we can rewrite that. I'll do that in a second. So then that entire limit which takes me just a second to write out. So remember, this goes to 0. Again, we're assuming that p is greater than 1 right now. This goes to 0. So we have negative 1 over 1 minus p. If I take that negative to the denominator, I could write this as 1 over p minus 1. So great. If p is greater than 1, this is going to converge, and it's going to converge to the value 1 over p minus 1. Fantastic. Now, let's look at the other side of things if p is less than 1. Now, if p is less than 1, then negative p plus 1 is going to be greater than 0. And if we look at the limit as b approaches infinity of b to this positive exponent, it's going to go to infinity, okay? So if this goes to infinity, so does this whole thing. And again, it just takes me one moment to write all this out. So it's going to diverge. So if p is not equal to 1, we have taken care of all the cases. If If it's greater than 1, it will converge to 1 over p minus 1. If that p-value is less than 1, then it's going to diverge. But what about when p equals 1? Well, let's look at that case. And the reason we're going to pull this separately is it doesn't use the power rule to integrate. If p is 1, and then I'll go ahead and rewrite it, then dx over x to the p is going to be the limit as b approaches infinity of the integral from 1 to b, and it's going to be dx over x. Well, like I said, this is not going to use the power rule to integrate. This integrates just to the natural log of x. So we're going to be looking at the limit as b approaches infinity of the natural log of x. We're going to evaluate that from 1 to b. So we end up with the limit as b approaches infinity of the natural log of b minus the natural log of 1. The natural log of 1 just goes to 0. So we're just looking at the limit as b approaches infinity of the natural log of b. Well, as b approaches infinity, that's also going to go to infinity. So this one will also diverge. So, in summary, what do we have? We can say that the integral from 1 to infinity of dx over x to the p is going to converge when p is greater than 1. And it converges to 1 over p minus 1. And if p is less than or equal to 1, it diverges. Now, please don't be alarmed. Most of the examples that we're going to work in this section are nowhere near as lengthy as this one, but we are going to use this function repeatedly. We'll see it even within section 8.8, but as we get into chapter 10, you're going to see it over and over again in there, and we're also going to do a lot of limits in there as well. So I wanted to take the time up front to go through this because it's something that we will continually refer back to.